The last part of this module that we're going to take a look at is the property of these materials and how do we determine why is something a great conductor of electricity or why does something not conduct electricity. And so we have to look at the electronic structure of these materials to get an idea, have to have a better understanding of the properties of these materials. And so for every orbital that we have, when two orbitals overlap, we need to have a bonding interaction and a non-bonding interaction. And that's what we see here in this orbital diagram. So I only have one orbital here. There's my one orbital. Well, when two orbitals come together to overlap, I have my bonding orbital and my non-bonding orbital up here. So for every orbital that interacts, you need to have one bonding and one non-bonding interaction. So as I go from 2 orbitals to 4, right now I have 2 bonding interactions, and then I have these non-bonding interactions. So now we split that one more time and one more time, basically to infinity, right? Imagine these large materials where we're putting together hundreds of thousands of atoms, hundreds and thousands of orbitals overlapping. You're splitting this energy down farther and farther and farther until essentially you can think of it as a band where we have 2 bands. We have one band where it's a bonding interaction and they're filled with electrons, and you have a band where it's a non-bonding interaction. Non-bonding or anti-bonding. And down here are our bonding. Because essentially we're going to just split this energy. We're going to split this energy finer and finer and finer, right, through infinity. And so as we get more and more molecules put together, with more and more orbitals, we're going to split that energy out thinner and thinner and thinner until we can just think of it as 2 blocks of energy. And so to get a better understanding of the properties of these materials, we need to look at the band gap of that material. And the band gap is essentially what is that energy difference between the valence band, where electrons are, and the conduction band, where electrons are free to move. So our band gap is the energy difference between the valence band and here's our valence band right here. That's our bonding band. And here's our conduction band. The valence band, that's where the electrons are located. Those are our bonding interactions, and the conduction band, those arise from our non-bonding interactions, our anti-bonding orbitals. And that's where electrons are free to move. And so this band gap is going to help us determine the difference in the behavior and the properties of a metal, a semiconductor, and an insulator. So in the metal, you'll notice that the valence band is directly connected to the conduction band. And remember, valence band is where we have electrons, and the conduction band, because it's our anti-bonding orbitals or non-bonding orbitals, there are no electrons there, but that's where electrons are free to move. So in order for something to conduct electricity, we have to be able to take an electron from the valence band and move it up into the conduction band. Well, in a metal, that's really easy because there is no band gap. Essentially, there's very little energy difference between where the electron is in the valence band and where the electron needs to go to move in the conduction band. So metals have very low, basically zero, band gap. Right? And as a result, we all know metals are great conductors of heat and electricity. And that's because it takes very little energy to move an electron from the valence band and push it up into the conduction band, kick it up into the conduction band where that electron is free to move. Because there is no energy gap, there is no band gap separating that conduction band with that valence band. Insulators, however, have a very large band gap. And so let's go back to that idea of here's my electron in the valence band. That electron needs to be kicked from the valence band into the conduction band so that it's free to move. But the downside, the only problem is that energy gap is so large, we'll never have enough energy to overcome that band gap. And as a result, that electron cannot go from the valence band to the conduction band, and insulators, subsequently, cannot conduct electricity. So insulators, very large band gap. Greater than 350 kilojoules per mole. And because of the large band gap, I won't be able to take an electron from the valence band and put it into the conduction band, and because of that, it's not going to be able to conduct electricity. Because of the large band gap, insulators are unable to conduct electricity. Right, the energy gap, we're never going to find enough energy to overcome that barrier of the band gap. The energy gap between the valence band and the conduction band is too large. So conductors, right? Like metals conduct electricity because it's very easy to take an electron from the valence band and move it into the conduction band where it's free to move. Insulators, on the other hand, do not conduct electricity because of this large band gap. We're not going to have enough energy to take an electron where it resides in the valence band and put it into the conduction band where it's free to move. So on the high side, we have insulators. On the low side, we have metals. Right in the middle, we have semiconductors. And these are actually really interesting to work with because they have a band gap, but it's not such a large band gap that it's insurmountable in the case of insulators. Semiconductors have a band gap between 50 and 300 kilojoules per mole. But what's important about that is that that's a workable band gap. We can come up with enough energy now to promote that electron from the valence band and move it up into the conduction band because semiconductors have a smaller band gap. Have a band gap between 50 and 300 kilojoules per mole. So metals don't have a band gap, so we cannot really control the energy required to push an electron from the valence band to the conduction band. Whereas with a semiconductor, because there's a band gap, we can modify this material to modify that band gap, to change how large or small that band gap is, and that would change the properties of this material. So we can chemically modify, and this is what's interesting about semiconductors, is that we can change that band gap. We can chemically modify this band gap by changing the material in the semiconductor. Right, and that's interesting because if we can change the energy right here, right, we can change the property. We can change how much energy is put in, or when that electron comes back down, how much energy is released by modifying this material. So this is a workable energy range, and not only that, we can tailor this energy range. We can change this energy range to fit the function that we'd like to use this semiconductor for. There are two types of semiconductors. There's elemental semiconductors, and what's interesting about elemental semiconductors, right, they all contain 4 valence electrons. So we'll see carbon. Most commonly we see silicon as a semiconductor. Germanium can also be used for a semiconductor, and then even one form of tin can be used for a semiconductor. They are a pure element. There's only one element in that semiconductor. So we're either going to have carbon, silicon, germanium, or tin. The nice thing about silicon is that silicon can be purified very easily, and silicon is very cheap, right? Think of sand. Silicon dioxide is sand. Sand is very abundant, it's incredibly cheap, and it can be purified to very, very high levels. And that's important because the purity of that material you're using for your semiconductor will determine that band gap. The slightest impurity can change that band gap, and that'll change the properties of your semiconductor. So you want something that's incredibly pure in your elemental semiconductor. The other type of semiconductors are compound semiconductors, where we're going to combine 2 different elements together. But if we'll take a look, an example of a compound semiconductor is gallium arsenide. So here's arsenic, and here's gallium. So if we look at gallium, gallium has 3 valence electrons. Arsenic has 5 valence electrons. So when you average those 2 together, we get 4 valence electrons. So that's what's kind of interesting about our compound semiconductors. We're going to average something together that has 3 valence electrons, something that has 5 valence electrons, for a total of 4 valence electrons. Just like with our elemental semiconductor, except for compound, we've combined 2 different elements together. And this is a way of doping. This is a way of changing the properties of our semiconductor by chemically changing the band gap by adding an impurity to our semiconductor. Right? This isn't Lance Armstrong in the Tour de France and blood doping. No, this is chemically modifying our semiconductor by adding an impurity. So chemically changing the band gap of a semiconductor by adding an impurity into the pure semiconductor. So where we're going to start is our intrinsic semiconductor. And our intrinsic semiconductor is the undoped state, right? Undoped state. The initial, right, undoped semiconductor. We want to be able to change this energy, because changing that energy will change the properties of the semiconductor. We want to make it a larger energy, a smaller energy. That's going to change the properties of this material. And so we're going to look at 2 types, N-type and P-type semiconductors that are made through doping. So the first type is N-type, and it's N for negative semiconductor. It's a negative semiconductor because we're taking something that has extra valence electrons. Remember, we're dealing with pure elemental semiconductors where we want only 4 valence electrons. So to make an N-type semiconductor, we're going to add an impurity to our semiconductor that has extra electrons. And so if here is our intrinsic silicon semiconductor with its 4 valence electrons, and that valence band is full, I cannot hold any more electrons. If I add some phosphorus to that has 5 valence electrons, I'm adding extra electrons. I do not have space for those extra electrons. Those extra electrons need to go up in the conduction band now, in my negative semiconductor, my N-type semiconductor. So we make that by adding an element with more than 4 valence electrons. Into our pure semiconductor. So what happens, right? The valence band is full. The extra electrons go into the conduction band. So we've changed that energy gap. We've changed that band gap. So we had a pure elemental semiconductor that had 4 valence electrons. That 4 valence electrons filled the valence band. And then we add a little bit of an impurity, right? Part per million level. So you do not need to add much. We add a little bit of an impurity that has extra electrons. Those extra electrons now have to reside in the conduction band because our valence band is full. But the important thing is now we've already got electrons in our conduction band. That's going to modify the band gap between the valence band and the conduction band. For the p-type semiconductor or positive semiconductor, we go the opposite direction. Now I'm going to take some aluminum. Aluminum only has 3 valence electrons. And I'm going to mix that aluminum into my silicon semiconductor. And what that's going to do is it's going to make holes. It's going to make openings in my valence band because now I'm mixing in something that has less than 4 valence electrons, and now I'm going to have extra space for electrons in my valence band. Because remember, here was my 4 electrons was silicon. Now I'm mixing something in that has less than 4 electrons. Now I'll have space in that valence band. So our p-type semiconductor are made by mixing an element with fewer than 4 valence electrons. Into the pure semiconductor. And what does that do? Mixing something that has fewer than 4 valence electrons creates a gap. It creates a hole now. But again, if we look, we've changed that energy yet again, because here is the energy level of my electrons, and here's the conduction band now. I've modified that band gap between my conduction band and my valence band. And we do that by mixing an element with fewer than 4 valence electrons. Creates openings. It creates electron holes, spaces for electrons to go. And it changes the band gap. So N-type, we have extra negatively charged electrons. P-type, we're missing a few negatively charged electrons. We're a positive semiconductor. And so where this comes into play and how this is used in LED lights, for example, and it's the similar process that's used in solar cells, is that we put those N-type and P-type semiconductors together. And that makes this PN junction, this gap between the P-type semiconductor and the N-type semiconductor. And so remember, the N-type semiconductor, we've mixed in some extra phosphorus. It's got some extra electrons, and so we have electrons in our conduction band. The P-type semiconductor, we've mixed in some aluminum that has 3 valence electrons, and that creates these gaps or these holes where we have space for electrons to go. And so here's our LED light. We apply a current to that LED light, and what it does is it pushes electrons out. It kicks electrons out of the conduction band. They have nowhere to go except for to fall into the valence band, to fall in the openings in the P-type semiconductor in that valence band. And so as those electrons fall from the conduction band to the valence band, they release energy, and they release energy in the form of light. And the light that they're going to release will depend on that band gap. So the larger the energy of the band gap, right, that light will be closer to a blue or a purple. The smaller the energy of that band gap, the closer that light will be to an orange or a red. But why are LED lights so efficient and such a good light? Because they provide a uniform source of light. So your traditional light has got a mixture of wavelengths. And so to get lights of specific colors, we put in filters to filter out certain wavelengths and leave you with only the wavelengths of light that you want, if you wanted an orange light or a green light or a red light. LED lights are much better in that they only have one band gap that'll produce one wavelength of light of one specific energy, an energy that's associated to that band gap. So we would get a more pure form of that light because all of the energy being released would be similar to a red light or an orange light or a blue light, depending on that band gap. Right, so here's some examples of LED lights for your Christmas lights, and all we're doing to change that color is we're changing the semiconductor that we're using, and we're changing that band gap within that semiconductor, within the N and P-type semiconductor and that PN junction. So red lights, for example, we see the gallium phosphide or aluminum gallium indium phosphide. We've mixed multiple elements together to make really unique semiconductors for that red light. And we can see it's a little bit different mixture for the green light. We've got gallium phosphide, gallium nitride, indium gallium nitride. So just by changing that composition, you're changing that band gap, and you're going to change the color that's given off. But what's important is you've set that band gap up. It's only going to give off one color of light, a much more uniform form of that light. So semiconductors in these LED lights, they're much more efficient than your traditional light, and they provide a much more pure form of light. So I know we covered a lot of material, essentially one chapter of material in the day, but the important thing from today's lecture are what are the 4 different types of solids available, right? We talked about metals and the properties of metals. We talked about ionic solids and their properties, covalent and molecular solids and their properties. We got to understand the differences between all 4 of those, as well as the differences between conductor, insulator, and semiconductor. And then how can we modify our semiconductors through doping? And then just kind of a basic understanding of what does that mean when I go put those semiconductors together and to make an LED light, and how does that dictate the color of that LED light? So this is the last of the lecture material. This is the last material we have to cover. This is the last material that will be on the final exam. So Wednesday, we're going to review only, nothing more, no more material. And then the final exam will be on this Thursday.